Hello, my lovelies. How is everybody doing? I can see lots of questions and worries about what NMR is in the chat. So I will first say welcome. Hello, I'm Georgia. If you haven't met me before, welcome back. If you have, I'm all right. Thank you for asking, Namrata. Yeah, I'm all right. So, hey, Jalaj. Those of you who are year 12, so I asked this is a year 13 topic, but it's an intro. So I asked on YouTube, I did a YouTube poll last week, which some of you answered, as to whether sort of the year 13s wanted this to be like the normal home working clubs thingy where we just answer questions, or whether we would prefer an intro to the topic so that the year 12s could come as well, and so that the year 13s could get a refresher. And the sort of overwhelming response was please do an intro. So this is definitely year 12 friendly. It's very much just an introduction to the idea. An NMR is a type of spectroscopy, so like mass spec, like infrared spec, but it's one you only come across in year 13. And some of it is relatively simple, but it can get quite tricky. So it's a good idea to sort of have an idea of it first. So it's a good idea for you guys to be doing it early. And we're only going to do sort of like, we're not going to cover everything to do with NMR today, just because there's not enough time. And then next week, I will sort of cover the rest of NMR. So you'll get a good grounding in it. It's an analytical technique. So that means that it's kind of organic, but you can use it for other things. So analytical techniques kind of come under a topic of their own, because you can apply them to so many other techniques, to like things in organic or inorganic. Is there a web class? Yes, there's a recap class at for today, Jalaj, but Felicity is taking it. So I'll be around, just make sure everything's okay. But Felicity is going to take the class at 4. But yes, so I shall get started then. Hopefully everything will be fine and you guys won't find this topic too terrifying. This is another one where it's going to be useful for you guys to download the booklet, because some of the sort of graph scales are like a bit small and I couldn't make them bigger. So if you need to see those, then I would download the booklet so that you can zoom in on the PDF. Where is this on the OCR spec? It's right at the end. So this is right at the end of all the specs. And this topic tends to come up sort of like with infrared spectrometry and with mass spec. So what you get is like these big questions that are like, determine what this structure is. And then they'll give you like an infrared graph and an NMR graph, or a mass spec graph and an NMR graph, or like some other information from like tests for ions and then an NMR graph. And you'll have to figure out what the structure is. So it's something that needs a little bit of practice, and it combines lots of other topics. So it's a good idea to have a bit of an introduction. Yeah, so as I said, if you've just shown up, this is an introduction to a year 13 topic. So it's year 12 friendly. Is this in the AQA spec? Yes, this is in OCR, EdXL, AQA. So again, this is a year 13 topic, but it's an introduction, so it is year 12 friendly. Can I tell Felicity to pronounce the name? Yes, I already explained. We talked about name pronunciations. So yes, and the class we're talking about for is on our platform, and I'll tell you about our platform a bit later. But let's get started properly. Cool. So I hope you have all downloaded the booklet. So this is our sort of NMR session, and I'm just remembering that my face always blocks things in the top right, so I'm really hoping I haven't put anything at the top right. Cool. So as usual, at the end, I'm gonna sort of like give you a coupon code for our website, where we've got lots of other classes, and you can subscribe to sort of attend those. I'm glad you're excited, Simply Bubbly. So yeah, stick around to the end to get that. Let's start. So there are two types of NMR that you look at A level, and they are the most common types of NMR spectroscopy. They are carbon-13 NMR, so that's an isotope of carbon, and there is proton NMR, which we'll come to in a bit. So we're going to start with carbon-13 because carbon-13 NMR is kind of the simplest. It's the easiest to understand, so that's where we're going to start. So you can see the graph on the left. I've dropped a molecule right on top of it. The molecule usually isn't in the graph, so that's not, usually there. Usually it's just the peaks. Does anyone know, are there any year 13s around that can tell me what is on the x-axis? What do we call the x-axis? What do they mean, an odd number of nuclei required for NMR? So what I'm not going to do, yeah, thank you, it's chemical shift. So what I'm not going to do today is explain the theory behind NMR, because that's like a whole other, it's a whole other thing. And I just wanted to sort of give an intro to the spectrum. So I'm not going to do that today, Jalaj, but we will get to that at some point. But yes, on the x-axis, we have something called chemical shift. And we're going to talk about what chemical shift is in a bit. And chemical shift is measured in parts per million and is represented by the symbol delta. So that's the same symbol as you would get for, same symbol that you would get for, when you write your delta negative or the delta positive, like the slightly, that's what you use for chemical shift. Yeah, so those of you who are saying centimeters to the -1 or inverse centimeters, that's what you use for infrared, not for NMR, but it's a good shout that you remember that. So we're going to talk about what chemical shift is in just a second. So each peak on the spectrum, of course, represents something. Does anyone, I will come to what chemical shift is in a bit. If it's the same units, why is it different? It's not the same units, it's parts per million. The units are parts per million. I'll come to what chemical shift is, don't worry, see me. Cool, so does anyone know what each peak represents? What is each peak sort of like, what's it telling us? Does anybody know? Fragment's not a bad guess, but it's not quite right. Carbon isotope, nucleus moving, environments. Yeah, environments. Okay, so each peak represents a carbon environment. And I know you haven't come across carbon environments before, so don't panic. Each peak is going to represent a carbon environment. So the carbon environment is about what kinds of molecules, what kind of atoms, what kind of elements are around that carbon. That's the kind of thing that tells you about the carbon environment. And the higher the chemical shift is, so keep in mind that on our diagram, 0 is on the right-hand side, so the high chemical shifts are on the left. The higher the chemical shift of the carbon environment there is, the more electronegative the adjacent atoms are. And do bear with me. So I'm going to show you sort of what I mean on the diagram. You'll get there in a sec. Just wait for it, Jalaj. I promise it makes sense. Okay, so if we have a look at this molecule here, we have a propanol. We have a propanol with the hydroxyl group sort of on the central carbon, right? So as I said at the beginning, this is an A2 topic, but it is AS friendly. It's an introduction. Cool. Yes, A2 level, but this is an introduction, so it's AS friendly. So the higher the chemical shift. So when we have a carbon, like this one in the middle that I've circled, attached to something like oxygen, that's very electronegative, that has a very high chemical shift. So this carbon here, the environment that it's in is an environment that is sort of very electron deficient. So if you guys think of it in terms of your partial positive, and you're partial negative, because that carbon is attached to an oxygen, it's in a very electron deficient environment. That's what we mean by carbon environment. What's attached to it? So that means its chemical shift is very high. So this peak here is the peak that is represented, that represents this carbon. Are you with me so far? Does that make sense? So a carbon environment is about what the carbon is bonded to, and the sort of electron deficient means high chemical shift. Yeah. So if you look at a molecule, each carbon is either going to be sort of like very neutral, or it's going to be partially positive, or it's going to be partially negative, depending on what it's attached to. So a carbon attached to an alcohol group is very electron deficient because the oxygen is very electronegative. Or a carbon attached to a fluorine is going to be very electron deficient, because the fluorine is so electron negative. So that carbon environment has a very high chemical shift. And chemical shift is just about sort of how electronegative the things that are attached to the carbon are. Does that make sense? So carbon environment is just like, what kind of things is that carbon bonded to? Does that make sense? Are we following me so far? So chemical shift is just a measure of the carbon environment. Sounds good? Yes? So you can work out the number of carbon environments for any molecule. Yes, exactly. So I'm going to put under chemical shift a measure of the carbon environment. So what does the number stand for? So as I've said, sort of in the middle box, the higher the chemical shift, the more electronegative the things attached to the carbon are. So the chemical shift is basically measuring sort of how electron deficient something is. Why are some peaks higher than the other? I will come to that in a second. Is that not an environment? Yes, it is. CH is an environment, and we'll come to that in a second. So we've talked about how the carbon attached to the oxygen is going to have a really, really high chemical shift because oxygen is so electronegative, right? So we need to think about the other two carbons. And as lots of you seem to have noticed, we only have one other peak. And we only have one other peak because the other two carbons are in identical environments, right? So both of them are attached to 3 hydrogens, and both of them are attached to another carbon that's attached to an oxygen. So the whole molecule is symmetrical. So if the carbons are bonded to exactly the same thing, then they're in the same carbon environment. Does that make sense? So if they're in identical environments, they will only be represented in one peak. Are we following me so far? We're good so far? So we get why there's only one peak. Yeah? Cool. Perfect. All right. So lots of you are asking me why the peak is higher. So that is what the last box is for, right? So you can see there that the second peak, the peak that is representing the 2 carbons, is doubly as high as the peak representing 1 carbon, right? And that's because the area under the peak, not necessarily the height, the area under the peak represents the number of carbons in that environment. So the area under the peak represents the number of carbons in each environment, and we'll sort of see why. So lots of you, but it's not a shape. It is a shape. You can kind of see, you know, at the bottom there, you can see that little sort of groove. It's because technically it's a bit like this. it's just sort of so close together you can barely see it. Does that make sense? So it is still the area under it, it's just very small. And we'll come to ones where it's not so tight. So in a little bit, we're going to be looking at things like this, which is technically one peak. So we have to think about the fact that it's an area, not a height. So getting used to that idea already. So like in the future, we're going to be looking at peaks that are sort of like wibbly. So it has to be the area rather than the height. But I see what you mean. It is minuscule for that one. But yes, so we have, you're confused about the last part, about the fact that the area under each peak represents the number of carbons. Is that the bit you're confused about, Jalaj? Are you too late? You might be a bit confused. We're going over, we're doing sort of an introduction to NMR. So if you've not covered it before, you might be a bit confused. Why is it carbon-13? Okay, so all I'm saying is that the area under, so I want you to imagine that the peak looks like this instead of a straight line. I'll talk about why it's carbon-13 in a second. So it's sort of like, if you zoom in really far, the peak's more of a triangle than it is a line. So it's the area underneath rather than the height that tells you the number of carbons in an environment. But when the peak's really skinny, it looks like it's just the height. Does that make sense? But it's technically the area underneath. Fat peak, roger that. Yeah, exactly. Let me know if that made sense, Jalaj. But do only carbons have peaks? Yes, this is a specifically carbon-13 spectrum. So the only thing in this spectrum are peaks involving carbon-13 environment. So not carbon-12. Carbon-12 doesn't show up on an NMR spectrum. So only carbon-13 shows up on an NMR spectrum. There are only certain types of nucleuses that you can do NMR with. And two of them are the ones you study. So you study carbon-13s and you study hydrogen-1, so normal hydrogen. Can you use integration from maths to find the area underneath? You don't need to, because most of the time the computer software does it. What elements can you do NMR with? Mostly protons and carbon-13s. So the peak, the higher the peak, the more carbon atoms in that environment. Yes. Yeah. Okay, is everyone cool for me to move forwards? We're going to have a go at sort of assigning, looking at a few more carbon-13 spectrums. Are we good to do that? Yep. Cool. All right, so I have two molecules here and two carbon-13 spectrums. And this is the time where it's quite hard to see the scale. So you might want to open up the PDF so that you can see the scale. But we're going to look at the one on the left first. So this is a skeletal diagram, so be aware of that. So these are all carbons. So if you feel confused about skeletal representations, I have kindly drawn in the carbons. So we have three peaks for this on the left. We have three peaks for the molecule on the left-hand side. And that's because we have three, so usually you're not given the molecule. You might be given several molecules and asked which of the spectrums belong to that molecule. Or you might be given the spectrum and then some other information and asked to figure out what the molecule is. But we're starting slow. Yes, so Kang says, so there are three carbon environments. Yes, there are three environments because we've got three peaks. And very kindly, this spectrum tells you how many carbons are in each environment just by putting a little number on the top. So carbon ones, always carbon ones. In a carbon-13 spectrum, yes. In a proton spectrum, it will be protons, but we'll come to that in a bit. So we've got three peaks, which means we've got three carbon environments. And I want you guys to help me decide which peak belongs to which. So we're going to start with this peak over here. So it's got a 1 on the top of it. So that means there's only one carbon in that environment. So which carbon is going to have the highest chemical shift? Yeah, it's the carbon attached to the oxygen, right? Because the carbon attached to the oxygen is going to be the most delta positive. So it's also going to have the highest chemical shift. And there's also only one of them attached to oxygen. So it makes sense, right? There's one carbon in that environment and it's the most shifted. Yes, exactly. It's the most electron deficient. So we've got our first carbon. In that case, we've got two other peaks. Both have 2 carbons in that environment because it says 2 on the top. So we know there are 2 carbons in each other environment. So which carbon is going to belong to this peak? So the highest chemical shift is the most electron deficient. Yeah, exactly. So the yellow is actually going to be the CH2s, not the CH3s. So the yellow is going to be these 2 carbons, right? Because they're like slightly more shifted than the last peak. So that's because they're closer to the oxygen. In the molecule, they're a little bit closer to the oxygen. So they're technically like a little bit more electron deficient than the CH3s. So they're going to be slightly more shifted. Does that make sense? And the molecule is again symmetrical, which means that they're in the same carbon environment. Yeah? Make sense so far? Cool. I'm glad you love chem. And that sort of only leaves us with the CH3s, right? The CH3s have to be this last peak. There's 2 of them that are in the exact same environment. So we've got 2 carbons in that environment. They're the furthest away from the oxygen, so they're the least shifted. Yes, exactly, Masimi. The closer you are to the electronegative thing, the higher the chemical shift in parts per million. So the lower the electron deficiency, the lower the value. Yes, exactly. You guys, you got it perfectly. I'm glad, Namrata. How can we figure out the molecule if you aren't given it from the spectrum? We'll come to that. There's more information. You can't just from carbon-13, just like with infrared spectroscopy, you can't figure out an entire molecule just from looking at an infrared spectrum. You can't figure out an entire molecule just by looking at a carbon-13 spectrum. I'm glad your mind is blown. It's a good day if I get to, blow some minds. All right. Last molecule on the right-hand side, we've got quite a big molecule there, and we've only got 3 carbon environments. And we've got we can see here that we have one of the carbon environments has 2 carbons in it. One of them has another 2 carbons, and then the last one has 4 carbons, right? So we've talked about the fact that chemical shift, the higher the chemical shift, the more electron deficient a carbon is. So on this molecule, which carbons are the most electron deficient? You can't see an oxygen, fluorine, or nitrogen. That is true. Why isn't CH3? Remember, Khadija, that we're looking at carbons, not hydrogens. So it's not the number of hydrogens, it's the number of carbons. This is a carbon-13 spectrum. Yeah, the double bond. An alkene is more electron deficient than an alkane. A double bonded thing is a lot more electron deficient. So the sort of most shifted peak belongs to these 2. The double bond is an electron dense area. The double bond is, but the carbons themselves are quite electron deficient. So the bond itself is electron dense, but the carbons are electron deficient. I hope that makes sense. Somebody just asked me something, but I can't remember what it was. Why is the alkene more electron deficient? Oh, you asked about ppm. Okay. So an alkene, if you think about it this way, the electrons are all coming from your carbon. You don't have sort of like a hydrogen coming in to sort of share electrons with the carbon. All of the electrons have to come from the carbon. So in terms of chemical shift, the carbon is more sort of electron deficient. What's the environment? The environment is an alkene. The carbon is in an alkene environment. Will they always give you the tiny numbers above? No, but I will show you what happens when they don't. We're gonna come to that. And you ask, what does parts per million mean? Parts per million is the unit. And I can't explain why parts per million is the unit without explaining the theory behind NMR, and I'm not going to do that today. How would you phrase the answer? Like if it asked what the carbon environment was, I would say it was an alkene carbon environment. Cool. I'm going to move on. So we've figured out what the first peak is. What about the next peak? There's 2 carbons in the next environment. Which carbons is that going to be? Yeah, the CHs. These here, so they're closer to the alkene, so they're a little bit more shifted than the other carbons, but they're sort of not too shifted. So so it's our CHs. And then the last one, we've of course got 4 carbons in one environment. Yeah, which are the methyls. That's our last one. So we've got those 2, which are in exactly the same environment. Those 2 methyls are joined to a carbon that is joined to an alkene, and it's the same with these. Those 2 methyls are joined to a carbon that is joined to an alkene. The whole thing's symmetrical. Are you guys with me? Does that make sense? So you start at the center and branch out? Not necessarily. You do in a symmetrical molecule, but not all molecules are symmetrical. Yeah, we good? Yeah, yes, you would start with most electronegative. Is there such thing as an aldehyde carbon environment? Yes, there is. And I was literally about to show you it. Okay, so we're not going to do much in the way of looking at proton spectrums because this always takes longer. No matter how much time I plan for NMR classes, it always takes me longer. I don't know why. But anyway, so we're just going to really quickly, just so you guys have seen them before, look at, so before we were looking at a carbon spectrum, we were looking at a carbon-13 NMR spectrum. The other one that you have to be able to interpret at A level is a proton spectrum. So that's a hydrogen 1 spectrum. And remember that we call it a proton spectrum because of a reason that my pen is going to let me. My pen hates me every time. All right, please. Pretty please, pen? No. Okay. Oh. No. Ah. Okay. The pen hates me. All right. Okay, we're back. We're back. The pen's back. Okay, so remember that a H, when you have a H plus, that is the same as a proton. So when I'm calling it proton NMR, please don't get confused. Proton NMR. So it's a hydrogen, but a hydrogen only has a proton and an electron. So if it doesn't have an electron anymore, it's just a proton. So I'm just going to do a very sort of like brief, have a look at this spectrum. Because as you might have noticed, instead of like nice sharp peaks, like in our carbon spectrum, we've got these like little clusters, right? That's technically one peak here, and this is technically one peak. So Proton NMR has like a whole nother thing that you have to be able to analyze. And we're not going to talk about how to analyze it today. I'm going to do that next Tuesday because it's quite tricky and it's the hardest part of NMR. So I just want you to have seen them before, because you guys were asking me why are we looking at the area under each peak as sort of like the number of carbons when it's basically a straight line. And it's not a straight line for Proton NMR. So you can see that you really couldn't tell how many protons are in each environment by just looking at the height, right? Because the heights sort of are kind of all over the place for each peak. Does that make sense? I'll come to TMS in just a second. But is everybody cool with understanding why I sort of originally said that the number of carbons in an environment is the area under the peak rather than the height of the peak? Because for Proton NMR, for H NMR, rather than carbon NMR, you have like these wiggly peaks. Yeah, it's sort of like by cluster, I mean like these. They're called splitting patterns, but we're not going to come across those. Clusters, just like the sort of like jiggle of peaks. The jiggly peaks, no, you will never have to draw an NMR spectrum. What does the height show? Nothing. I mean, like, you can kind of tell from the height-ish that there are less carbons in one environment compared to another. But it's the area under the peak that's really important. So somebody asked what TMS is. There's no y-axis. No, because it's the area under the peak rather than the height. So you can't really use a y-axis. All right, I'm going to just really quickly talk about TMS and then we're going to finish off. So you guys, as I've said, that chemical shift is a measure of sort of how electron deficient each carbon environment was, or in terms of protons, it would be the proton environments. So TMS is the reference compound. So we set TMS, which is tetramethylsilane, as sort of like 0, because it's very much not electron deficient. It's very electron rich. So everything else is compared to TMS. Where is TMS? It's here, where the arrow is. So it's just set at the 0 for chemical shift. But that's all we're going to do today, because all I want is you guys to have an idea of the introduction, and then we're going to carry on with this on Tuesday if you guys want to. Or if you guys are like, that was pointless, I don't want to know that yet, then we'll do something else. Yeah, it's a bit like a control. Yes, it's like zeroing you know, when you use my brain's gone, colorimeter. You know, when you use the colorimeter and you like zero it, that's essentially what TMS does, something like that. You want to do this? Up to me. Are we finishing now? Yes, we're going to finish off now because I don't want to overwhelm you guys with information. So we're going to leave it here, and I'm going to sort of do the usual thing where I tell you all about the website. Why does the chemical shift axis on the proton have a smaller range than the carbon-13 spectrum? Oh, Jake, for that, I would have to explain the theory behind NMR. And as I said, I'm not going to do that today just because I don't want to complicate things, because I know that people get really sort of panicky about NMR. So I just want to do stuff basically. I want to just like do a nice introduction, and then have you guys like absorb the information, and then I'll sort of add to it. Can we finish this slide off? No, I don't think so, because this slide is kind of like, it starts us on the Proton NMR bit. So I'd like to finish off with carbon NMR, give you an idea of what we're going to look at next time. And then we can do it next time. But I'm going to finish. What do the numbers on the graph show? Those are your chemical shift. and they're all comparative to TMS, just like how all of your masses are compared to carbon-12. But I am gonna finish it. Otherwise, it's just gonna get complicated. I'm so glad it's helping me, Meh. So there'll be a session with NMR questions. Yeah, if I keep doing NMR, then eventually we'll do some like exam questions, but they do get complicated. They get quite hard. I would argue this is the hardest part of A-level chemistry, arguably. But yes, so if you haven't seen the website before, then I'm about to do that thing where I show you it. If you've seen it before and you don't want to subscribe and you're just happy with the YouTube stuff, then you can head off, or you can just, watch me talk. Is it next Tuesday? Yes, it is next Tuesday. Yeah, we'll continue with NMR next Tuesday. But yes, I'm going to show you the rest of the website. Because that is part of the reason I do these, so that like we can show you what we do. So the next NMR is next Tuesday? Yes, yeah. Because I was going to do year 13 stuff just like the normal way, where I ask questions, but then not enough people, sort of the year 13s have sort of wandered off a lot. So we're just doing introductions to things. Yes, we will do some past paper questions, but the past papers are, they're a lot harder than what we covered today. So I just want to like edge us into them and then we'll get there. But yes, anyway, so if you've seen the website before, I'll say goodbye to you. If you haven't and you want to know more about like the things that I do and that we do, then stick around and have a look. So this is our website. I think it's pretty. So essentially what we've tried to do is think of what somebody who was doing an A-level might need to sort of learn, and then we put it in one place. The thing that's happening at 4 is on our website, Emma, rather than on YouTube. So for example, if you were an AQA student for A-level chemistry, you would have, yes, the session has finished. I'm just doing the usual, here's the website, sign up if you liked this and if you want more help. So you would sort of like scroll down to whichever topic that you wanted to study. So like, let's say you're unsure about your ideal gas. You would first do a diagnostics quiz to see sort of like how you're doing. And then you would sort of watch videos about the things that you were bad at in the diagnostics quiz. So you could like skip sections that you're cool with and just do the bits that you're bad at. And then you would sort of like do a quiz again to sort of like see how you're doing. And then you sort of know if you've learned the things properly or if not. And then you could run through sort of exam questions in the video. So we've got sort of exam question run through so that it's sort of not like a mark scheme where it's very sort of dry and confusing. It sort of explains why you're writing the thing in the mark scheme that you are. So that is the next thing we do. And then we also have exam packs. And the exam packs sort of have a bunch of exam questions that we've written sort of when you run out of the exam questions sort of in past papers so that you can sort of do those. And then sort of you answer the question yourself and then you can view the solution and mark it the way you would mark your own exam papers. And then the last thing that we have going on the website is me and like sort of the other subject heads. So we have web classes. So in about 20 minutes, a new colleague of mine is going to be taking a calorimetry class, and I'm going to be sort of around and making sure everything's cool. And then sort of like there's a book club and personal statement writing workshops and classes on different topics. So those are all listed. And then you can watch previous classes that we've done. So there's still me. Hello. Why is amides in the schedule? Are we not going to do year 12 sessions on YouTube? Yes, we are. I just haven't changed it. So like originally we didn't know whether the year 13s would drop off or not, but they've sort of disappeared a bit. So it's going to still be a year 12 friendly thing. And we also have on the website drop-in sessions where basically you come in and just ask me things you're confused about. So we've got a bunch of drop-ins happening in the week. So that's basically our website. And I think it's good. And if you would like to sign up, then have a click through. My lovely colleague has just sort of dropped the link in the chat. But yes, what other AS classes are we going to do? I don't know yet. I had a schedule, but it included year 13 stuff. And so now I'm kind of having to rethink the schedule. So next week, Tuesday, we are going to sort of carry on with this topic. And then on the Thursday, I'm not sure. I might put out a poll on YouTube or Instagram and ask you guys what you want to do, or I might just do something that I think you need help with. But next Tuesday, we're definitely going to carry on with this topic. But yes, so as promised, I know this one was shorter, guys, and there's good reason for that. I don't want to overload you. Make sure you set reminders for all of these things. And here is your nice code. You don't have Insta, please put the poll on YouTube. I will put the poll on YouTube if I put a poll up. But to that, I can just ask you what you feel like doing because you come to the classes on the website. So I can totally just ask you. But yes, I will put the poll on YouTube. Okay, lovelies. Thank you for sticking around to the end. I know this one was shorter and I know it was slightly different and a bit tricky, but you guys did super well. So well done. Well done for that. I hope it was useful.